Hey everyone, Chris here. I thought I'd give you a bit of an update on the GenFEAx engine and where we're at. So what you're looking at here on the screen is ConnectFEA. This is a structural steel connection of a shear plate bolted model. And it's a very basic steel connection, but what we're going to do here is we're going to compare results between the back-end Calculix engine that ConnectFEA currently uses compared to the new one we've built into GenFEA, our custom .NET 10.0 solver with a .NET 4.8 bridge. And the result's pretty spectacular. So what you can see there is we've got a bunch of contact mechanics set up, a bunch of tie elements, and we're going to run the analysis here using that Calculix solver, and we're going to time it. So we want to check two things. We want to see the time it takes and obviously the accuracy we get out of it. So right now we're not starting the timer because ConnectFEA is building the mesh and it's compiling all the surface contact back-end stuff for the solver, and once the solver starts then we start the timer. So you can see the timer is running there. I sped this up a little bit so you don't have to watch the entire process, but it runs fairly quickly, just under 40 seconds, like 37 and a bit seconds. So let's call it 38 seconds. And from this we can see we've got our output, so that's a displacement on the entire connection model. We can of course isolate that, but we'll do it later. And you can see at the top there we've got a scale multiplier of 100, so this is exaggerated 100 times. But okay, that gives us a good reference benchmark. So now we jump over to the sample code using the new GenFEAx engine. And we're going to do the same thing. So we'll bring up the timer there, we'll reset it, and then I'll click start and very quickly click on the volumetric button. And this is going to run the exact same model. So we're using the exact same connection, same loads, same contacts, same ties, everything, and we're running it. You can see the debug output's quite detailed. It gives us a lot of streaming output. It'll also finalize with the summary of forces, resulting forces, and contact forces and all of that. So that's really good. You know, building a custom solver just means you've got so much more control over it. Now it's not plugged into ConnectFEA yet, so it does write out an FRD file, the same as Calculix. So we can see that's the one I just created now. I'm going to open that results file up in trusty old SolidFEA, which can load FRD files, and we'll look at the results. So off the bat we can see that looks pretty good. Of course the exaggeration scale there is now set to 81. You know, doesn't really matter, it's just a visual output, but what we're looking at is those contours and those values. So we can see that we are achieving similar results. So we can see the output and the deformation of the connection results look similar between the two. So let's isolate some components. So this is our column element there, profile 1, and we'll do the same here. So we saw that we had a value of 0.04 there in Calculix output with ConnectFEA, and we can see we get exactly the same with the GenFEAx output, and the contour maps match between the two perfectly. If we look at stresses, so this is the von Mises stress, we can see what those contours look like, and we're going to do the same here in the Calculix output from ConnectFEA, and again, you know, it matches perfectly. And then if we isolate some of the other elements there, we will see that, you know, the results are looking pretty good. We're getting consistent, reliable outputs with the contact mechanics, the ties, the loading, etc. So that's quite exciting. It took about 50 seconds for GenFEAx to solve this model, so it's slightly longer than Calculix. Remember, Calculix running in C++, with an MKL Paradiso solver backend, in the .NET one that we've built, also running with MKL Paradiso backend. Obviously, you know, we do things a little bit differently with GenFEAx. We've built in actual components, not just to spit out raw results, but also to give us a real-time output streaming, and then the ability to isolate results much quicker after the fact. So we can programmatically extract element outputs, contact face forces and contact forces between them. We can extract values sliced through the bolt elements, for example. So if you want to look at shear planes and extract results through connectors like the bolts there. We can do that, and so on and so forth. So that's pretty exciting. This is only supporting 4-node tetrahedrals at this stage. We will build in the 10-node tetrahedrals and hexahedrals at some point in the near future, but this is looking really exciting. Hope you found that informative, and talk to you guys soon. Cheers. Bye.